Okay, so welcome back to another video. So in today's video we have an infinite sum here. So we have the infinite sum from n is equal to 0 to infinity of 2 to the power n divided by 1 plus 2 to the power 2 to the power n. So the exponents is, I wouldn't say necessarily nested, but at least there is some continuation there with the exponents in a sense. But this is not going to be that difficult to show since the result of this comes out very nice, and you'll see why soon. So to start this off, I would like to observe that the following function 1 divided by 1 plus x is, let me fix that for a second. So 1 divided by 1 plus x is actually equal to 2 divided by 1 minus x squared, and then minus 1 divided by 1 minus x. And you can see this by, so I'll consider this function, so 2 divided by 1 minus x squared. Simply, I can decompose this using some partial fractions. So it means this can be decomposed to, let's see, this will be, this denominator will be 1 minus x, and this will be 1 plus x. You solve for your constants for a and b. So let's see, b 1 minus x, that's equal to 2. So let's see, if you set you set x equals 1 here, b will be 0, and then this will be 2. So then a will be 1, and then over here if you let x equals -1, a will be 0. Let's see, 2. So b will be 1. So if we plug our terms back, so let's see, 2 1 minus x squared is equal to 1 minus x, and then plus 1 divided by 1 plus x, and then simply I'll just I'll subtract the 1 divided by 1 minus x to both sides, so we get that 1 plus x is equal to 2 divided by 1 minus x squared, and then minus 1 divided by 1 minus x. So that kind of just proves this little observation here, of course. It's just considering a functions, but this function will work, as you'll see why later. So now in this case, how about I let our, we'll do the little substitution. How about I let x equals 2 to the power 2 to the power n. So with doing that substitution, you'll see that our infinite sum n is equal to 0. So see, 2 to the power n, and then divided by 1 plus 2 to the power 2 to the power n. So we get our new sum is that, so I'll factor out the 2 to the power n. And so with that we have 1, or rather we have, 1, because I factor out the 2 divided by n, or 2 to the power n. So we have 1, and then divided by 1 plus x squared. So 1 plus x, I mean. And then we can actually use that substitution. So from over here, so that means I'll put this as 2, and then divided by 1 minus, so I'll put this in parentheses, 2 to the power 2 to the power n squared, and then subtract that with 1 divided by 1 minus 2 to the power 2 to the power n. Okay, good. So now, evaluating some terms, well, from the parentheses, I mean. I won't distribute this just yet. We'll get to that in a bit, but for now let me just simplify some things out. So inside, so we have 2 divided by, so this is 1 minus, let's see, 2 to the power n squared. Basically, this is just 2 to the power n multiplied by 2, so it's be written as 2 to the power 2 to the power n plus 1. And then we subtract that with 1 divided by 2, or 1 divided by 1 minus 2 to the power 2 to the power n. Now with this, now we can actually distribute the 2 to the power n into our inside expression. So therefore, doing this will yield us, this will be 2 to the n times 2, so that means this is 2 to the power n plus 1. And then the denominator still stays the same. And then we subtract this, distribute the 2 to the power n, so 2 to the power n divided by 1 minus 2 to the power 2 to the power n. Now, next thing we want to do is because we're evaluating this series, this infinite series, let's actually rewrite this in a way that I can actually write this in terms of partial sums. So really what I'm going to do is I'm actually going to take the limit as capital N approaches infinity of our partial sum. So our lower index is still the same, but now our upper index is n, where we set n approaches infinity, of our series. So just write the same thing as before, 1 minus 2 to n plus 1, okay? And then subtract that with 2, and then divided by 1 minus 2 to the power 2 to the power n. Now with this, let me actually evaluate some terms. So let's see, the limit n approaches infinity. Okay, so let's start off with our lower index, n is equal to 0. So when I do this, we get, let's see, we get this is negative 2, and then let's see, plug 0 here, so we get divided by 3, and then add this with 0, so that's 1, and then divided by 1 minus 2, so that's 1. Okay, now add this, so now start with our next index is 1, so let's see, if I plug 1, get negative 4, and then over here, so this is 1 minus 2, and that minus specifically just comes from the denominator, because you're going to get a negative term from here, no matter for what you plug for n, for some natural number n. We'll start with n equals 0 and so on and so forth. So from here, let's see, 0, 1, 2, that means we'll get that this is 15, right? Let's see, 0 plus 1, or 1 plus 1 is 2, so 4, and then, yeah. Okay, and then next is, this will be plus, and then plug, well, hold on, first, I don't want to jump the gun just yet. We'll put the minus, then plug 1 to here, so we get 2, and then divided by 1 minus 2, and then so this is negative 3, so that'll change that to a positive. Okay, by one more term, and you'll see, and I say one more term just because like this is an infinite series. So let's see, we plug n is equal to 2, so we get this is 8, and then divided by, let's see, 3, so 8, 2, where this, so that's that'll be negative 255, so that means this is a negative out here, and then I'll add this with so 2, so this will be 4, and then divided by let's see, 1 minus that would be 15. Okay, and then so on and so forth. I could write out for n, but you'll see that if you pay attention closely, this is actually a telescoping series. So you'll notice that this term cancels with this term, this term cancels out with this term, and then this term will cancel out with the next term, all the way at the next one when n is equal to 3, so on and so forth. Okay, and okay, so we know that this is series is telescoping. So then this means the limit as n approaches infinity of this entire of the partial sums, so n is equal to 1 of so 2 n plus 1 divided by 1 minus 2 to n plus 1, and I'll subtract that 2 to the power n, and then 1 minus 2 to the power 2 to the power n. We'll see that this is just equal to the limit as n approaches infinity of 1, and then plus, so this means the right term will still be available, so that'll still be positive. Like I said, the terms cancel from the first, and then each on and so forth. So you're just left with 1, and then plug capital N into here, so 2 to the power capital N, and then divided by 1 minus 2 to the power 2 to the power capital N. You'll notice that over here, this, if you compare the degrees, this is a lower degree, and then over here from the denominator, this is a higher degree. So meaning if we were to take the limit as n approaches infinity, we're taking some smaller number and then dividing by some larger number. So you'll see that this is actually going to converge to 0. And so therefore, we can conclude that the limit of the partial sums is equal to just 1. And therefore conclude that this infinite series is simply just equal to just 1. All right, nice. That's pretty cool if you ask me.